right. Well, welcome to the session on extending functional pipelines with gatherers. My name is Venkat Subramaniam. We'll talk a little bit about the pipelines. We'll talk about a certain intermediate versus terminal operations. So we get the basics really good before we dive into it. And then we'll talk about how we can use this feature to extend those pipelines we already know about, and what are some of the features available as well. So let's get started. We're going to first talk about the pipeline. Well, Martin Fowler calls this the collection pipeline pattern. And I think this term is not being used as much as it should be. But if we want to think about the functional programming aspects in Java, the Stream API, it's a good idea to start really thinking about pipeline. For example, one of the things to think about the pipeline pattern is, this goes back to the fundamentals of imperative versus functional style of programming. Let's take a look at an example to understand what this really means. So let's say we are interested in computing the total of double of all the even numbers. So you could use the imperative style, and you could write code like the following. You could say, for example, result is equal to 0. You can start with that. You can output the result in the very end when you're done with it. But within this pipeline, you could say for, and you could get the elements in this collection. So you could say for an element E, coming from the numbers, and we'll spare the effort of using I equal to 0, I less than syntax. We can use the for each, and we can say if element mod 2 is equal to 0, meaning it's an even number, we can say result plus equal to element times 2. So this we are all very familiar with as the imperative style of programming that we all have used over and over before. So this one here is essentially the imperative style, where we loop through and perform the total of double of all the even numbers. However, if we want to use the functional style, you could say how this would look like. So in the functional style of programming, we often think about, if you will, you could say a data transformation rather than, I would argue, data mutation. So essentially, you are thinking about this as a transformation of data. There are times when you could take your solution and more easily convert to a functional style. There are times when you have to put in a lot more effort and get to the point where you're able to do it. So in this case, we could say result2 is equal to, we could say numbers.stream, and using a stream API, we could do a filter operation, and we can say if the element is an even number, then select it, otherwise go ahead and discard it. Then we could do a map operation where we could take the element and then double the value, as we can see. And then finally, we could say sum the operation. And in this case, because sum is an operation on integers, you could ask it to transform to an int. And then, of course, eventually you could, output that value, result2, which should be the same as the value from the other computation as well. And we can see the result is 60 and 60. So this is a imperative style versus a functional style. Again, this is something most of us are very familiar with since the time this was introduced. However, if we focus on the functional style for a minute, this is where I mentioned earlier that Martin Fowler calls this as the collection, if you will, pipeline pattern. So essentially, that's why I like to use the word pipeline. And so essentially, the idea here is that you have a collection of data. In this case, numbers is the collection, but you are interested in looking at this pipeline operation. It turns out that this is a very common operation we are all used to, but we may not sometimes recognize it. So for example, if you're on a Unix-like system, you could do a cat on some file. So we could say some file. You could do a grep of some word you are interested in. You could then do an awk or a sed, if you will, of some sort. And then potentially you could use something like a WC to look at the number of lines and so on, or whatever operations you want to perform. So if you look at it, this is of course a source of data, but as we recognize it, the grep in the Unix pipeline is really a filter operation. So we've been using the filter quite often, just like how we use a filter here. The grep becomes the filter to pick some data, but to discard the things we don't care about. And you can then continue further and look at this as a map operation. It's performing the transformation of the data. And then eventually you could say things like WC or like your reduce operations. So this is something that's been around for a long time. And we all have used this on Unix systems, if you will, where we use a pipeline. And that's where the concept of these pipes really come in. So we know that these are the pipes. But the difference here is that it's a pipeline, all right, but what is it a pipeline of? So it is a pipeline, if you will, of functions. So essentially, it's a pipeline of functions because the filter is a function, the map is a function. That's what these things are. It's a pipeline of functions. And you could say through, you could argue, which data flows. So essentially, through this pipeline of functions, the data is flowing. So another way to think about this is you could be sitting in a room and you can have air that flows in, and you can have a purifier. And a purifier is essentially like a filter, and you can have a heater with winter approaching, and then you could have the air flow into a room. Well, that's a pipeline too. So when you get the fresh air from the outside purified, and a heater is heating and warming your room, that's a transformation. So the heater is a function. The job of a heater is to take cold air and to put out warm air. It's a heat transfer function. A purifier similarly is supposed to, send only things that are pure. That's the whole idea behind this. So thinking about this as a pipeline. Now that we talk about this pipeline, you may ask the question, why should we care about this pipeline? Can't we just, write the code in a traditional way? One of the reasons why this is really helpful is, I'm going to say that imperative style of programming, I would argue, has higher accidental complexity. This is one of the reasons why we tend to really move towards a functional style of programming, because imperative style often has higher accidental complexity. There are two types of complexities we often have to deal with. One of them is the inherent complexity. Well, that is from the problem domain, from the application. So if you are writing a code for an airline reservation system, or you're writing code for insurance business, or you're writing code for a medical application, there are, or worst of all, the tax applications, right? I never wish my enemies to work on that. So the point is, when you have to write those code, there are complexities that come from the problem, the application domain. But accidental complexity, unfortunately, is not from the problem. Accidental complexity comes from the solutions we choose. And these can be reduced, if not eliminated, by using a different solution. Well, as it turns out, functional style code, you could say, reads like the problem statement. So this is one of the a statement. This is one of the benefits, if you will, of the functional style. It becomes easy to read through the code. So given the collection of numbers, get me only the even numbers, transform them to the double, and then total it. So you're just reading through it, and becomes a lot easier to work with it. So that's one of the reasons why functional style reduces the accidental complexity, becomes easier to work with as well. But having said this, one of the challenges with a functional style is to understand what the consequence of the code we are writing is. And as it turns out, don't assume that all languages deal with functional programming the same exact way. So for example, Let's say you're programming in a language like Ruby. Again, don't think that I'm not a fan of Ruby. I'm a huge fan of Ruby, but at the same time, it's important to understand what the consequences of using these languages are. In a language like Ruby, when you use a functional pipeline, it will create intermediate collections in every single pipeline stage. So what that means is, if you have 7 stages, you end up creating 7 different collections. Now, the disadvantage of that is you are creating 7 collections to discard 6 of those 7 collections in the end, because you're only interested in the final result. So what does languages like Java do? But more important, what does functional programming languages really do? And this is something we need to really keep in mind. So I'm going to say functional programming is 2 parts, if you will. One is functional, if you will, composition plus the use of lazy evaluation. So to me, these 2 are very important parts of functional programming. Languages like Ruby and JavaScript, for example, give you the function composition quite a bit, but they don't give you lazy evaluation. However, lazy evaluation is extremely important for us to be able to do functional programming. But why is that? And the reason is, I would say, functional programming in general, you could say, relies on a lazy evaluation for efficiency. So this is extremely important to have, because without lazy evaluation, it's going to be more garbage being created. If you create more garbage, you have to spend the time collecting more garbage as well. It may not be very efficient in running. So this is one of the central behaviors you would expect from the functional programming ideas is lazy evaluation. So what does it mean to have lazy evaluation? So in order to understand that, let's go back to this code for a minute. We have the filter and a map and a sum, but let's change this problem just a little bit for us to look into it. So let's go ahead and get rid of that. We have a filter and a map right there. But after we do the mapping, let's just say we are interested in finding the first one. So I'm going to say find first. And in this case, I'm going to get the first value. We'll say result is equal to, and let's output the result in the very end. So in this particular case, it's an optional of 0. Well, optional because you may not have any elements at all in the collection. That is, are no even numbers. So we have the result in the very end. However, one function you could use here is a function called peek. A peek function is useful for debugging purposes. It allows you to take a peek at what is flowing through this pipeline. So you can say, in this case, system.out println, and you can ask it to print it. But what is really interesting about this peek is, if this was done naively, what would have happened is you take all the 10 values in the collection and you're transforming the 10 values here. So if you were to take this original collection, this is flowing through the values 1 through 10. So as a result, when you filter it out, you're going to be sending out of this the value 2, the value 4, if you will, the 6, the 7, and the 10 as well. Well, once you do that, you're going to transform this data. So as a result, you may get, in this case, 2 times 2 is 4. This becomes an 8. This becomes a 12 and a 16 and a 20. And eventually, the find first is going to take the value 4 and return it, and discard, if you will, unfortunately, the words numbers 8, 12, 16, and 20. But imagine if you had to do this work yourself, how upset would you be if most of what you created is thrown away and only the first value is being kept? That would be rather very inefficient, isn't it? Well, that's the beauty of lazy evaluation. It doesn't perform any computations that it it doesn't have to perform at all. So this is not the way, thankfully, the application runs, the code runs. So in this particular case, this is one of the things we need to realize quite a bit. So the stream does not, this is important to know, evaluate a function for each value in the collection. So this is not the way a stream actually executes. This is one of the things I really enjoy in programming. I often say the syntax is what you, I would say, what you look at. The semantics, I would say, is what you, I would say, should, is probably good to add, see. So this is why programming is interesting for me. Syntax is what you look at, but the semantics is what you should be seeing. So this code syntactically is telling us something different from what it actually does, which is semantical about it. So the stream does not evaluate a function for each value in the collection. But what it instead does is it first fuses, if you will, fuses the functions in the pipeline, if you will, into one combined, or you could say composed function, and then evaluates the composed function, function, but only, you could say, only on demand or as little as necessary. So this is a fundamental when it comes to Stream API, is how it evaluates it. So as a result in this case, it is not plowing through the values 1 through 10 right now. Instead, it says, I'm going to take the 1 and I'm going to fuse these two functions together. So the filter and the map have been fused internally, and it says, hey, 1, let's apply that on the fused function. And that says, gosh, it's not an even number, discard it. Well, what about 2? Oh, that's even, let's transform it to 4. And the minute it's transformed to 4, it goes to the next function, find first. And the find first says, gosh, thank you. I just wanted the first value. You gave me a first value. Thanks, I'm done. We can go home. So the minute find first signals we can go home, the rest of the pipeline does not get executed. So as a result, when you run this code, you notice the peak showed 1 and 2, but it never touched 3 all the way up to 10. Well, that basically is the concept of lazy evaluation. So in this, just to illustrate this a little bit more, if I were to go back to this code, and rather than storing this into a result, let's go ahead and say I want to just keep that in here as a find first. And then, in this case, let's go ahead and simply say done in the very end. So when I run this code, you can see it printed the values right there and are done. Those are the results from the peak command, but peak stage. But what if I were to simply comment this out? So this is where the difference between intermediate operation and terminal operation really comes in. So these two are, or rather these 3 are intermediate operations. This becomes the final operation. So the key thing that we need to keep in mind here is that in the case of stream, intermediate operations are fused, but not executed unless a terminal operation, you could say, triggers it. So the triggering has to happen from the terminal operation. So in this case, even though these were fused, there is no terminal operation to execute. So when you run the code, it simply printed done. It never displayed the result of peak. If you bring in the terminal operation, then you see the result of peak, but not otherwise. That further illustrates the laziness in this computation. So essentially the idea here is that intermediate operations are lazy, and we got efficiency by the way of how they actually postpone computations. So what's the benefit? The benefit is efficiency. We are not performing operations whose results are never going to be used, and operations are performed minimally only to the extent they know. So you may think about this, what's the big deal? And the answer is, you need to really think about the operations you perform and the amount of data you're going to create, the garbage you're going to create, and also the consequence of doing it. So let's step back and think about this as an example, how this would look like. So I'll use a little bit of a trivial example to think about this, but I think one that would probably make sense. So, I live near Denver, Colorado, and it's a big airport, but oftentimes I want to go to places where I very rarely have a direct flight. I often go to this beautiful city of Oslo. Well, there is the chance of me getting a flight from Denver to Oslo is exactly zero. So I don't think there is any airline that actually flies from Denver to Oslo. If they did, I can board the flight in Denver, maybe 11 hours later, boom, I could be in Oslo. That would be very, quick, right, relatively speaking, for the 11 hours of flight. But life is not that easy. So I leave Denver usually and I go to Newark, and I'm in the Newark airport for anywhere from 2 to 4 hours. And I would go from Newark airport all the way to Frankfurt, if you will. And I have to tell you the secret, Frankfurt Airport has the best showers, I can tell you that. So usually I land over there, I got 4 to 5 hours, you go take a shower, freshen yourselves, and then another 2 hours of flight, you are in Oslo. But by the time I'm done with it, it is literally 24 hours versus 11 hours. Tough luck, right? So the point really is, if you have to land and take off, you're wasting at least about 4 hours each time. That is assuming the flight don't get delayed, which is even worse. So would be nice not to have to make these stops. Well, guess what's going to happen? If you take a stream API, you perform the operations and you do a terminal operation to get a result, if you will. And then once you get the result, you take the result, we'll call it as a R equal to, and then on the result, if you were to say R dot stream again of some form, right, and then you perform more operations, that would rather be inefficient because that's like me landing in Newark or Frankfurt. But on the other hand, if you can eliminate this part and get all the way to the terminal that's in here, well, the good news is if you can get rid of that part, then you are just flowing through the pipeline and you end up with the final result once that'll be rather more efficient. So in other words, intermediate operations, if you're able to leverage them, gives you better performance and efficiency, both in space and time, not just in time alone. Now, of course, you could argue, what if my data size is really, really small? What if the computations are really quick? What if the garbage is not that big a deal? And I think it's very important to consider those things. Don't go overboard and devise solutions for the perceived performance and gains, and in doing so, complicate your code a lot more. So we always have to weigh that in deciding what direction to go. So having said this, well, let's go back to Java 8 for just a minute. Well, in Java 8, we already had a capability. So in this case, as you can see, we have some intermediate operations, and we have a terminal operation right here in the end. But what if you don't want to just find the first operation? What if you want to do something else? You could do a collect, for example, and you could do a grouping by of some sort. So you could have called methods like that. These really allow you to do some custom operations, special operations rather, in the terminal phase. But you say, you know what, none of that really helps me. I've got a business need. I want to perform some operation that is not done in the JDK. How can I actually do that? Well, you can knock yourselves out by implementing, if you will, the collector interface. So essentially, if you look at what the collect method is taking, you will notice the collect method is taking a collector as an interface right there. So because it's a collector, you can implement your own collector in here, and as a result, you can dive into that particular collector and implement your own collector interface. So right from the days of Java 8, we had the ability to implement our own custom terminal operation. But the question is, what if we need to implement our own custom intermediate operation? So we were able to do stuff towards the end. But what if I want to do something in the middle that is my own operation? And the answer to that until recently was good luck. So you couldn't really do your own custom operations. Now, we could pretty much say what they have provided for most part is more than adequate. So the number of times you may actually need to implement your own custom operations is not that many. But if there is a time when you want to do it, there was no real good way to do it. As an example, if you had this collection of data, and I want to simply say for each, let's go ahead and print out system.out and print line like so. Well, in this particular example, as you can see, we are printing the results of this operation as we go through, and if I execute it, you can see from the output we got the values which are the even values in this particular collection. We are taking those even values, doubling them, and we are printing them out. So that's the output of this code. However, again going back to Java 8, you were able to do this already in Java 8. You can say limit, and you can say limit this to 3 values, not all the values in the collection. So as you can see, this is displaying 5 values. But if I were to provide limit 3, you will notice the output contains only 3 values and not all the values. So this was quite possible. But back in the Java 8 times, I would actually get email from people saying, hey, I saw your video on the streams, collections API. I like it. But, right? People don't say, I like it, thank you. They always say, I like it, but, right? But anyways, I like it, but I want to only produce values until a certain condition is being met. But here's the problem. In a for loop, what would you normally do? When a condition, right? When a condition is met, we can call break. Well, functional programming does not have break. So there's no break statement. In fact, that's exactly the reason. Break is a statement. In functional programming, we don't use statements. We use expressions. There's no break expression, right? The break is a statement. So functional programming does not have a break. So what gives? How do you break out of a loop? And in Java 8, so what if we want to break out when, right? If and when you could say the value is greater than, let's say a value greater than 5. How do you break out of it? And the answer is in Java 8, good luck, right? So there was no way to do that. What would you have to do in Java 8 is you produce the entire result, and you have to discard values you don't care about. There was no real good way to do it. So my responses at the time was, really sorry, right? You don't have a way to do this, and there was no effective way to break out of a loop. So if this was Java 8, how would you have solved that problem? And the short answer is to create the entire solution and then loop through it again and take the values you want and discard the rest. Not very efficient, as you can tell. But thanks to evolution of Java, starting Java 9, we have this thing called take while. So take while is a very helpful function. So you could say take while, you could argue, is the functional programming, right? So is a functional programming evolution. So essentially, functional programming equivalent of imperative style break. So take while is your break in functional programming. So what you can do here is you can say take while the element where the element is less than or equal to 5. So when you run this code, you can see we got a 4, but without it, obviously, it's going to give us all the results. But now we are saying, I want only values that have not exceeded 5, and that becomes a take while function. So take while is something that they added in Java 9 much later than what was provided in Java 8. Now we can see the issue here, right? We needed to do something that was not done in the Stream API, and we had to wait for them to add into the Stream API in Java 8. Similarly, more functions have been added along the way, but a lot of them were to the terminal operations, not to the intermediate. But what if we wanted our own custom intermediate operation? So if we wanted our own custom intermediate operation, how do we make that happen? So there are maybe two answers to it. One is, sorry, you cannot do it. So you have to really use the complete result, then do post-processing, which is not the most elegant, but if it's not going to be an issue in performance, you may live with it. But the problem is, anytime you want to do some operations like that, you got to keep working on these multiple steps, and you were like, my gosh, wouldn't it be so nice to have a intermediate operations we can add without having to really do the post-processing. The second option is, you could make a request and say, could you please provide this for us? Well, you could make a request if what you want as a custom operation is actually general enough for others to benefit from. They may eventually consider and add that to the Stream API. And even if they were to add it, you're not going to get it for a year at least, right? So, but remember, we never want something a year from now. We wanted it yesterday. So how do you really have things that you need yesterday and you cannot wait for it? So that becomes a pain as well. Wouldn't it be nice if we can add our own custom operations? Well, this is a feature that was implemented by Victor Klang, and essentially the idea was to be able to add your own custom intermediate operations. So that basically is the whole idea of gatherer. So a gatherer is, so what is a gatherer? Let's talk about it. So a gatherer is a way for us to add our own custom intermediate operation to a functional pipeline, essentially to a stream, right? So essentially, you want to take a stream pipeline, but you want to be able to add your own custom operations into the pipeline. So that is basically the idea of the gatherer. So the gatherer is a way for you to add your own custom intermediate operation to a functional pipeline. So the question is, how do we actually do that? But before we talk about it, let's talk about a few different things. So you have a pipeline, and your business says, we need to be able to take this data and perform this operation, and how do we do this? And you're like, let me see if I can do that into my filter map and so on, maybe a limit and so on. I can bring that in. So the first and foremost, how to do that. So the first and foremost, my recommendation is this. I am not a big fan of raining in somebody's parade or party, right? People are genuinely excited, genuinely interested. But at the same time, though, when you see somebody getting overly excited and do things they shouldn't be doing, it's also your professional responsibility to, kind of alert them and say, dude, we don't need to do this. So this is a little sad for me, but I get emails quite often from people who get excited about stuff. And excitement is good. I'm a guy who gets excited about stuff, almost all the time. But this person sent me an email saying, ooh, look at this. I came across gatherers. Here's a problem, and I want to solve this problem, so I use gatherers, and sends me the code. And I had to painstakingly reply to the person saying, I'm really sorry to tell you, you could have solved this problem with a call to filter and a couple of calls to map. You didn't have to write the gatherer. This is one of the things I alert you, because if somebody gets excited and says, ooh, I could use gatherer, that could be a danger sign, and I have to be careful. So the first and foremost thing I would recommend is see if you can solve the problem, I would say, using the existing functions of the stream, of the stream. So basically say, you want to solve this problem, don't try to reach for the gatherer just yet. Can you solve this problem by using things like filter, map, and whatever you have? Can you get this job done? And if the answer is yes, I can solve it using existing functions, save yourselves the trouble. And so this is one of the things I want to emphasize. To know how to write code is knowledge, right? When we love knowledge, and of course, to avoid writing it is wisdom. And I always want to emphasize both of those, right? It's not enough. So I would say knowledge, if you will, in general, without wisdom is dangerous. So you probably know those people, right? Who know how to do things, but very dangerous people to work with. They create more mess than you need to deal with. So and I would also say this is also experience. Young programmer goes to work to write code. Experienced programmer goes to work to delete code. So you are like, I want to reduce this code. I don't want to write as much as I can. So don't get too excited about gatherers and ask the question, do I really need it? If I don't need it, don't spend your time writing it. You say, all right, I don't have a way to really write this. Using the existing Stream API, what should I do? The second step is see if there are built-in gatherers that can do the job for you. This is yet another suggestion I really have. If you have a built-in gatherer, I would rather use that, because it's always better to use a function than to have to go create one all by yourself. So that's a lot better, isn't it? So if I go here to Java, I can say gatherer, and you can see there is a gatherers sitting right there, and gatherers dot, and you can see some built-in functions sitting right there. So when a new version of Java comes out, take a second to see if by any chance they maybe have added a few new functions. If they've added a few new functions, that's always good to use them than to create our own functions, right? So right now there is not a whole lot, but there is a function called window fixed. So what is the idea of window fixed? Well, the idea of window fixed is if you have numbers, let's say collection of data, let's just say you have 1, 2, 3, 4, 5, and 6. Well, windows fixed is going to do the following. Let's say I say a window fixed of 2. It would emit from the pipeline 1 and 2, and then it'll emit, basically, in this case, 3 and 4, and will emit 5 and 6, and so on. So essentially, those are the groups of data that it's going to start emitting. So in other words, in the functional pipeline, if you take this collection, it's going to send you 1, 2, and then send you 3, 4, and then send you 5, 6. So it's going to emit those in that window, and it's going to simply say, here's the window, and the next window, and the next window. On the other hand, if you were to use a window sliding of 2, you would do 1 and 2, and then the next thing it would do 2 and 3, meaning it'll slide the window. And then it would send you a 3 and a 4, and then the next slide it would do a 4 and a 5, and so on. So it's simply sliding this window in terms of the values it's going to emit. So those two functions are already available. There's a map concurrent, which allows you to perform map operations using a virtual thread. And you have a fold. And you may wonder, what's the purpose of a fold after all? So essentially, in this case, if I were to use a reduce function, a reduce is a terminal operation. And when a reduce is done, it gives you that one result, and you're done, you're out of the stream. But what if you want to do the reduce, but you want to continue processing the stream at the end of the result of reduce? That's exactly what fold provides for you. So a fold is a reduce that's turned into an intermediate operation. But we'll get to a few of those later on, and I'll talk about scan as well a little later. So the point is, see if there is a built-in gatherer that can do the job for you. You say, you know what? I don't see a built-in gatherer. I cannot implement this using any of the traditional functions of the API as well. What should I do? You're like, I've got to implement this business logic. I need a gatherer. What can I do? My sincere recommendation is call a good friend. And call a good friend and say, hey, you know what? I've got this thought in my mind that I have to write a gatherer. What should I do? And your friend most likely says, let's meet for dinner, let's have some drink. Take it, right? And let's hope they will walk you out of doing this. And that's what good friends do, right? So essentially they say, you don't need to write gatherer. There are better life in your things in your life to do, and I recommend not to do it. Take their advice. Don't write the gatherer. You would have a better time moving forward. So call a friend, good friend, take their advice, right? But you say, I did, but still, right? That did not work, right? So you're like, I tried to talk to my friend. They couldn't convince me, right? I'm still inclined to write a gatherer. What should I do? Get really strong coffee and dive in, right? So this is going to require all the caffeine you can find in the world, because this is going to require some real deep thinking to get it right. And that's what we're going to see here today. And I had 2 doses of coffee before I came in, so I'm all set for handling this. And I hope you are too. So essentially, let's walk through and see what it takes to do this. So let's talk about intermediate operation in this case. So let's talk about this operation we are all familiar with, and we will kind of expand it to something a little different. So if I have, let's say, result is equal to, and I'm going to output, let's say, the result after all. So here is the result I want to output, right? Okay, so but what is this result I'm interested in? We can say numbers.stream.reduce, and to the reduce operation, I say 0, comma, integer sum, and I'm going to ask it to perform the reduce operation on this. You would notice the result of this is really a value of 55, but what just happened here? Well, the nature of reduce is, some languages, they call it as a fold left. So you start at the left and you roll forward by performing the operation that is given right there, which in this case is a sum. So the idea behind this is you're going to start with an initial value of 0 and you're performing the operation of plus. But in this case, you're going to bring in the first value, which is 1. And so you take the 0 and the first value, which is 1, and the sum of those two, the result, as we know, is a 1. You take that, and then you perform the operation with the second value in the collection, which is 2. And I'm going to make this a little small so it's easy for me to show this here. So we have a 2. So 1 plus 2 is a 3. And then we take that value, perform the operation on the next value, which is 3. And as you would expect, the result is a 6. And on that, you're going to perform the operation plus again. But this one is on 4. And so the result of this is a 10, on which you perform the operation one more time, but this time using a 5, and the result is going to be a 15. So when you execute this, the result is 15, but that's how it's computing that value in the reduce operation. So essentially, it's plowing through the values, iterating through every single value, but performing the operation on the partial result that is moved forward in the reduce operation. But what you receive in the end is literally that last value 15, as you can see. Well, that's great. However, some languages and you could say and libraries have a function called scan. So what in the world is a scan function? Well, a scan function, I would say a scan is a chatty reduce. So a scan function says, I am going to be walking through this collection as reduce is working, but remember, in the case of a reduce, you literally got as an output, so the output is 15, which is the last value. But that's not what scan does. Scan is very chatty. It's eager to tell you what's going on. It says 1, and then 3, and then 6, and then 10, and then finally 15. So it pours out, it spits, it emits the intermediate values along the way. So languages like Scala, Kotlin have a scan method. You also have reactive libraries like RxJava have a scan method as well. Why would you need something like a scan? The reason you need something like a scan is, as the data is being received and processed, you may want to keep updated certain output, or you want to continue processing while you are performing this calculation that you are interested in. So imagine you are computing maybe a running average as an example. So on your display, you want to show the current value and the average also. Well, if you wait for a reduce, when everything is over, you see the final value and the average. But that's not going to help you if you want to keep this updated on your screen, for example, while the computations are happening. Imagine you're showing election results. It would be kind of silly to wait for the entire thing to be over to announce a result, right? There is more excitement to show the results as things are happening. So you want to continuously emit the current data, but also the process data as well. So you want to not only compute the sums as you move through the collection, but you want to keep emitting the partial sums as well. But what you emit is your business. You don't have to emit only the sum. You could emit as a tuple the sum and the current value. And as a result, you can say, this is the latest value that I received, but this is the sum until this point, and it's up to you exactly what you want to emit. So the question is, how do I do scan? But keep in mind that scan is a chatty reduce, but scan is intermediate operation and is a chatty reduce, which is a terminal operation. This is another big difference between the two. So scan is an intermediate operation. So while reduce is terminal, scan is intermediate. So notice the reduce here is the end of the computation, whereas scan is going to sit right in the middle. So how do I use the scan after all? So let's go back to this and say result is equal to, well, actually in this case, let's just simply say numbers.stream dot for each system.out, and let's do a print line. This is going to print all the values 1 through 5, as you can see, right? But what I really want to do is the following. I'm going to just separate these so it's easy to see where the difference is. But I'm going to say dot gather. So a gather function is what you call for an intermediate custom step you want to add in your functional pipeline. You can call filter, you can call map, you can call various other functions, but you want to perform an intermediate operation which is custom, you call the gather function. So what do you do in the gather? In the gather, thankfully, you can simply say gatherers dot scan, and you can simply say start with the value 0 and do integer sum operation. Now let's contrast this to the code you see up here. This one here is a reduce operation. This one here is an intermediate operation, not a terminal operation. So the scan method is going to start emitting, if you will, it's going to start emitting the intermediate sum operations as it is happening along the way. So if I were to run this code, you notice that 15 in the top and you see the 15 in the bottom. So the end result is the same, but it's emitting the value 1, the value 3, and 6 and 10 that we saw as intermediate values in this computation. That's why you see 1, 3, 6, and 10, which are the intermediate values in that particular operation. So the scan function literally is emitting the intermediate values along the way. Like I talked about, you don't have to emit only the sum operation. You could perform the sum, but you can emit a tuple if you want to, right? Like a record. So that way you can say, here's a current value, and here is the sum value, and you can keep emitting that value as well. So there is quite a number of things you can do. So if you have an application where there's a stream of data coming in, and you want to do some processing on the stream of data, but you also want to keep sending out the latest value and the currently computed partial results, this can be really, really helpful to keep emitting that. So scan is a very powerful operation, but thankfully, that's already available to us as a built-in gatherer, so we don't have to implement it. So that is the nice thing, is you can just use the scan operation like so. Well, similarly, just as an example here, let's go back to the same collection, numbers.stream, and then I'm going to say gather. And in this case, you can say a fold. So gatherers.fold, and you can bring the fold function right there. You can see there's a supplier and a by function after that as well. So I'm going to say fold takes a value of 0 right here. And then I'm going to say integer, let's say a sum operation I want to perform as well. And then dot for each system.out and the print line. So if I execute this code, notice it's 15. And you're like, duh, why would I want that 15 through a fold when I could have used a reduce? Well, the idea here is you're not done with a stream. It's an intermediate step. So there is more stream to do after this if you really wanted to. So as a result, you can go back here and do a filter or a map or whatever that you want to do, so you can continue on this operation. Depending on how complex this stage was, there is more you can do afterwards as well. So what does this mean? So we can kind of summarize this, right? Scan, you can scan is an intermediate, you could say chatty you could say reduce, right? That's what it is. Scan is an intermediate chatty reduce. On the other hand, fold is an intermediate, if you will, reduce. That is the only difference between the two. So scan is a chatty intermediate reduce. So it says, I'm going to keep telling you everything that's happening, right, along the way. When a fold is just an intermediate reduce. It doesn't do anything different than reduce other than just accumulating the values, and it just emits the result value rather than being a terminal operation. It's an intermediate operation. So that's basically an example of using a built-in operation, a built-in gatherer that's already provided, and you can make use of that. Now, this is a good point to leave the room if you don't want to take any more pain, right? Because this is a lot of fun, but it's a lot of pain as well. So now comes the gatherer. So what can you do if you want to implement your own gatherer? What are you going to do? Well, before we go that route, we need to understand a few different fundamentals, if you will. So let's say we have data, and you're going to send the data using a stage 1, and you're going to send that to a stage, let's say 2, and a stage 3, and so on, until you get to the terminal stage. So this is where we need to take some time to really think through things we may not have spent the time thinking about in the past. This happens a lot to every one of us, right? We are working, we call this abstraction, because if we get to know everything, we're not going to survive, right? At some point, we're going to say, I don't need to know that right now. So it's quite possible we overlook some of these details. So let's logically think about this, right? So let's say we have a terminal stage. The terminal stage is a for each. If it's a for each, what does for each say? For each says, keep giving me values, and for every value you give me, I'll take an action, like printing things out, saving to a database, whatever that could be. So a for each is going to give you, take everything you give it. There is no limits to it. But what about find? So for each, you could say has no limits, right? So for each says, I'll just take whatever you give me. You give me 10 values, I'll take it. You give me 20 values, I'll take it. I'll just keep taking what you give me. So a stream is going to push the data, and that's going to transform through this pipeline, and the value ends in the for each. That is the destination. But what about find first and find any? Find first and find any, what do? Find first is expecting a particular ordering. Find any doesn't require ordering. That's the only difference between the two. But what do these two do? Both, right? So these two, right, are satisfied when, right, basically in this case, satisfied when one value reaches them. So the minute the first value hits a find first, what does find first say? Oh, thank you so much. I'm very happy. That's all I need. I don't want any more. So logically speaking, what's going to happen? These two functions will let the upstream stage know not to send any more data. So that's basically one thing we need to really keep in mind. So this is a revelation we need to keep in mind. In a stream, you want to keep in mind, data flows downstream and control flows upstream. So this is a concept we need to keep in our mind. Like I said, a lot of things we take for granted, right? Why? Because we're not the ones doing this stuff. So we're just using this, we don't have to think about it. But data flows downstream, control flows upstream. So in other words, the find first is saying, I got one data, please don't send me any more. And the previous state says, oh, you don't want it anymore, thank you, I will pass that information upstream. And that control keeps progressing upstream and eventually hits the source, for example, and the source says, oh, you don't want any more data, I'll stop pushing. And I will close the stream at this point. So that communication has to happen in a stream. This is why, if you go back to this example here, you can see that when we write numbers.stream.peak, and I'm going to say system.out, let's say print line, and I'm going to say a map, and given an element times 2, and then I say find a for each, right? So for each, system.out, let's say print line, and I'm going to print it out. In this case, you can see all the values you can peek, 1, 2, and so on, are just flowing through and giving you the results and all those values. However, if instead of this, you said dot find first, and then you said over here a stream dot for each and system dot out print line, and you're going to print it, what's going to happen in this case? When you run this code, you can see 1 and 2, but not anything afterwards. What just happened? Well, this printed 1, and the 1 was transformed to 2, and that was the first one, and we printed 2, but the find first immediately said to the map, hey map, I got one value which is 2, I'm happy, don't send me anything more. And map is like, oh thanks, find first, let me communicate that, and goes to peek and says, peek, don't send me any more. And peek is like, oh okay, hey stream, don't send me any more, and the stream shuts down. So that's the control flow versus data flow. And so the for each tells this in the opposite, find first goes that in the opposite direction and tells the map, which tells the peek, which tells the stream. That is something we need to keep in our mind, is that the data is transferring in the other direction. So having said that, now let's understand what's going to happen in this case. So not only that, there is yet another detail we need to be familiar with, and that is, what if we have, looking at this, we may think that, terminal operation is the origin of a control flow. Not at all. That doesn't have to be. For example, what if we have a limit before a for each? Well, remember, for each doesn't generate the control to stop the flow. For each is like greedy. I'll take everything you give me. But on the other hand, what if you had a limit before the for each? Well, what does a limit do? So the limit, right? The limit method, receives in this case as many data as it needs, and sends a stop signal to the upstream once that limit is reached. So essentially, if you go back to this code, you have a for each, as you can see here. This is going to just print all the values as it did, but I'm going to say dot limit in this case, and I'm going to limit this to, let's say 3 values, right? So if I run this code, you can see it printed only a combination of 3 values in the output. How did that happen? Well, the limit said to map, hey, I got 3 values, stop, don't send me any more. And that control flow goes back. Similarly, if you use a take while, and if you said take while, given an element is less than 3, what will take while do? It'll keep getting the values. The minute the value is more than or equal to 3, it sends a stop signal to the upstream. So the concept we need to keep in mind is that the data flows downstream, control flows upstream. So that is something we need to keep in our mind. Great. So now that we saw all of that, let's talk about how this can be implemented. Before we dive into implementing it, a gatherer represents a stage as we can discuss. So if you're implementing a stage, what do you have to do in your implementation of this stage? So in your implementation of this stage, you're going to say, some concepts you want to keep in your mind, right? Some concepts. First is element. So what is an element? An element is the data that is flowing through the pipeline. So you have elements, and you take an element, you do whatever you want to do with it, right? So what does the stage actually do? A job of a stage. The other thing you need to keep in mind is a downstream. So what is a downstream? Downstream, so element is the data, right? That's what it is. What is a downstream? This is a reference to the stage downstream. So essentially, you have a stage 2, you're getting a data to process, but you also have the next stage, stage 3, you have a reference to the downstream. So literally you have a reference that says, here you go, if you walk through the door, you'll keep going downstream in this pipeline, right? So to stage 2, stage 3 is downstream. That's a reference. There is one more that you will deal with, which is called the state. The state basically is the data that is used by the stage. So this is thankfully optional. So the other two are not optional, this one is. And we'll get to that a little later and see how we can make use of that. So given this, what is the job of a stage? The job of a stage is receive element, process element, that depends on your business logic for the stage, optionally push transformed data to next stage. So that's your job, right? You receive the element, you did the processing you want to process, and optionally push the data to the next stage. Why is it optional? Some stages don't push the data, right? For example, filter may or may not push the data. Limit will not push the data after it reaches the limit. So things like that. And then, ask the downstream if it wants more data and pass that on to upstream. So this is your job as well, to get this information from downstream and pass it to upstream. So this is the fundamental logic, what you have to implement, right? So now you know why I said you don't want to do this unless you really have a good reason, because that's something you got to think about quite a bit to do it. So your job is to say, I got an element, I do what I want to do, I push it downstream. Hey, downstream, do you want more? Okay, thanks for that. I'll let the upstream know about it. And you're going to pass that logic, the control, back to upstream. That's your implementation. So the question is, how can we implement this? And in order to implement it, just as a warm-up exercise, I'm going to implement a custom filter. The only time you ever implement a custom filter is after saying nobody should implement a custom filter, right? Because filter is already there. There is no reason to implement a custom filter. So this is just as an exercise to learn how to actually do this. So if you find anyone implementing custom filter, you got to take them to the parking lot and talk to them, talk through to them not to ever do this again, right? So, and right after this talk, I'll be exiting the parking lot as well. So essentially, this is just an example for us to play with. So let's go ahead and take a look at an example and see how this is going to work. So let's go ahead and say the output better be exactly identical, right? So numbers.stream dot for each system dot out print line, but here is our filter. Given an element mod 2 is equal to 0. So there you have it, right? That's the built-in filter as we know it, and you can see the values 0 through 10 being printed, which are the even numbers in this collection, right? So that's what we have. Great. Now we want to implement our own custom filter. So stream and then for each, we'll do a for each, and this is system out print line as you would expect. However, we're going to call the gatherer. So the gatherer is our custom implementation. Now, how do I implement a gatherer? If you look at the gather function, it has a gatherer as an interface. Just like, right? So as you kind of get the picture, right? So a collect is terminal, and collector can be collector is an interface to implement, you could say implement custom terminal step. Now, gather is intermediate, and gatherer is an interface to implement, if you will, custom intermediate step. So that is the parallel concept that you have in here in terms of how this relates to. So just like how you would implement a collector for collect, you would implement a gatherer for gather. But we all know how much fun it can be to start implementing interfaces. And the minute you start implementing interfaces, you got a bunch of methods you have to implement. You have to worry about, do you have to override the default method? All of them can become really messy. Well, this is where, again, I really appreciate what they have taken care to provide. There are factory methods that you can use to easily implement a gatherer without going through the steps of implementing a full-blown interface. So to do this, you can go ahead and call a gatherer dot and methods like off and off sequential. So you can call this method gatherer.off or gatherer.off sequential. So these are factory methods. Look at the return type, gatherer. Look at the return type, it's hiding, it's gatherer. So essentially, it is returning a gatherer. Now, before we go further, let's talk about this real quick. So there is a gatherer dot of sequential and gatherer dot, you could say gatherer dot off. So of sequential, sequential and of methods. So what in the world these methods mean? And why not of parallel, right? Why not have parallel? Why sequential and why off? It's very important to understand what these two functions actually do for us. These are convenience functions. They help us to get things implemented, but we need to understand what this means. So to understand this, let's step back again. This is why basics and fundamentals are so important to get this right. So let's step back to the basics. We can do one of the following, right? You can say numbers dot stream, or you can call numbers dot parallel stream. Now we also know you could have said numbers dot stream dot parallel. So I'm not going to talk about that option because that's kind of equivalent to running a parallel stream. But the point really is that in a sense is, the point is the following. You can have one of the following. A stream, you could say, may run sequential, or a stream may run parallel. How syntactically you do it is not really important. So you can have a sequential stream or you can have a parallel stream. Now, in a sequential stream, every stage runs sequentially. That's kind of near trivial, right? You know that. If it's a sequential stream, stages are going to run sequential. So you have your pipeline, and data flows through the pipeline, while the next data flows, the next flows, and that's pretty sequential. Nothing really exciting. So how do I create anything for this? We'll come to that in a minute. In a parallel stream, any stage, right, may run sequentially or in parallel. Just think about that for a minute. You have a parallel stream, but a parallel stream doesn't mean every stage has to be parallel, right? For example, I have a filter. I have a map. What do you think, your gut feeling? Will filter run parallel or will it run sequential? Parallel, thank you, right? Because a filter has no concerns. A filter simply says, given a data, I send it or I stop it. Map says, given a data, I transform and send it. So there's nothing it is restrictive on that. But in your parallel stream, right in the middle, you have a distinct operation. Or you have a sorted operation. What do you think is going to happen now? It's got to be sequential, right? Because if you say only send values that are distinctive, whoops, I got to know I received this value and know to send it or not. I cannot just throw that out in parallel because the other thread may be seeing the same value as my thread. I got to synchronize it. So more than sequential, it's got to synchronize it. On the other hand, a sorted, you can run things in parallel, but the sorted says, come on over here, let's work on this together, let's do the sorting, now you can go parallel. So I want you to think about this like an hourglass, if you will. So when you look at an hourglass, the top of the hourglass is big, sand can flow through the hourglass, but then this part is thin, and then the bottom is bigger. So all these things have to flow through this thin glass before it can go away in the bottom, right? So even in a parallel execution, you got this, so to say, point of a stage where you got to line things up. So hopefully that gives us a better idea, right? So off means run the way the stream is. Sequential, right? For a sequential stream, if you will, and parallel for a parallel stream. So that it's that simple. So off means run the way the stream is. Sequential for sequential and parallel for parallel. On the other hand, off sequential means run sequentially in a parallel stream. So why? Because I can't just throw things in parallel out. Now you know why they don't have off parallel. Because you cannot suddenly say, woo, I'm parallel, right? If you're in a sequential stream, you cannot just become parallel. So that's why you don't have off parallel. So off, I'm going to be whatever the stream is. You're sequential, I'll run sequential. Parallel, I'll run parallel. Off sequential, I'm sorry, I can only run sequentially. So if you're on a parallel stream, I want you to come here, merge through this, and then you can go forward after that. So that's the two functions that are available in the gatherer for us to use. So you can say gatherer a dot, and you can see the off and off sequential. You know what the purpose of those two are, that you can create them based on where you are going to execute it in this particular case. So that gives us an idea how these things manifest and how we can make use of it. So that basically leads us to essentially the implementation here. How are we going to do? So in this case, I'm going to say gatherer of, and what am I going to provide to this gatherer? Remember the three things we talked about, right? The first is state, but this is a filter. Does a filter have a state? What do you think? No, right? Big filter says, I'm just going to be putting my blinders on. You give me a data, I either send it or I block it. Hey, what about the value you saw before? What do you mean I saw before? I don't see anything, right? I only see one value that is going through. So state is not present. Now in Java today, there is a beautiful symbol for I don't care. And that symbol is underscore. And if you see underscore, I don't care. Underscore is one of the best variable names ever, in my opinion, right? It is meaning I don't care about it. In the past, I used to use the word ignore. That worked until I had to ignore two things. And now I had to say ignore one and ignore two. That felt really dirty. You can use underscore any number of times, right? Underscore, 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 meaning I don't care about anything. This is the best life ever, right? I don't care about anything. So, but you eventually have to care about something. So in this case, gatherer of, and what are we going to do with this gatherer is the question. So you're saying, I don't care about a state. I have an element, and I'm going to have a downstream that I'm going to be interested in processing as well. And you bring those three into it for us to use. And we are going to implement our custom step in here. But it's also a nice synchronization point, I think. So it's a good time for our break. When we come back, we'll dive in and see how we can implement it. So see you in about 15 minutes. Thank you. All right. I hope that was a good break. So let's start where we left off. So we talked about the off and the off sequential. Just to reiterate, the off will behave the way the stream is meant to. Sequential for sequential, parallel for parallel. Off sequential says, hey, if I'm in a parallel execution, sorry, I cannot do this parallel. I've got to do the sequential. That's what this off is giving us, right? So back here, I'm going to say gatherer off. This is a filter, custom filter that we want to implement. So what do we want to do in our gatherer, right? So I'm going to say custom, let's say filter, and I'm going to say given an element mod 2 is equal to 0. Let's start with that. So we'll take baby steps towards it. So this is going to implement the custom filter that we are interested, and it takes a predicate which is exactly the same as this predicate right here. So we're just mimicking the filter, right? So the custom filter, what are we going to do? So let's implement the custom filter. So we are saying, I want a gatherer, and the gatherer is going to be of type integer in this case. You can make it a generic if you want to, right? Nothing stops you from doing it. The question mark here is for the state. We don't care about it right now. And then we have an integer, which is the response we want to give. What does the custom filter take as an argument? It's going to take a predicate of integer, and we'll call it as a predicate, right? So that's the predicate we are taking as an argument. So it's time for us to implement our custom filter. Now, as you can see, our custom filter is returning a gatherer right there. So what do I do to implement this gatherer? So return, we can say gatherer of, and to the off method, we can say, I don't have a state, I have an element, and I have a downstream that I want to take as an argument. Well, okay, so what are we going to do to implement this downstream? Before we implement it, one of the things I want to emphasize here is that it takes quite a bit of discipline to write good code. And one of the problems, really honestly I say this, is people, partly to be blamed like me, who take shortcuts to do demos, and by way of that, maybe accidentally, we cultivate bad practices in people's mind. And when we cultivate bad practice, that is contagious. It grows quickly. And all of a sudden, you're at work scratching your head, and you got this unmaintainable monster somebody created. And you're like, people don't write bad code because they're malicious. People write bad code because they don't even realize it's bad code until it's too late. So here's one of the things I often tell that we should not do in general. And it's tempting to do the wrong things sometimes, right? So here is a recommendation I have, and that is, I often say that lambdas, I'm going to say lambdas are glue code. 2 lines may be too many. So this is a recommendation I follow quite a bit. So lambdas are glue code. 2 lines may be too many. I don't know what that was. So, okay. So essentially, lambdas are glue code. 2 lines may be too many, right? So they essentially, right there. So this is one of my recommendations. Lambda expression should be glue code. 2 lines may be too many. One of the things I discipline myself to do is not to write multi-line lambdas. Now, this reminds me of an experience I would never forget. I was teaching a course on functional programming in Java in the UK, and on the Monday morning when I went there, I said, hey, we're going to learn about these things. And one of the person in the room said, oh, welcome over here to our company. Just so you know, we all hate lambdas. And that was very welcoming to know that I'm going to teach about functional programming to a group that hates lambdas. In the middle of the day, I mentioned lambdas are glue code, 2 lines may be too many. And the minute I mentioned it, I could hear I have ruffled some feathers in the room. And during the break, one other person called me and said, let me show you something. And he opens a source code, and he shows me the code, and he says, the person who introduced lambdas to my team is not in this training, but here's the type of lambdas he wrote and why we hate it. And he shows me the code, and every single lambda is 70 to 150 lines long. And you can imagine why they hate it. This company had a very good culture of writing automated tests. He pulls up the code coverage, green everywhere except red spots. And he says, go click on any red. And every single red was a lambda expression. So the point really is, if you write bad lambdas, well, then people get really upset and they don't like lambdas. Poor lambda didn't have anything to do with it, right? It's we writing lambdas really bad. So when you write multi-line lambdas, it becomes really hard to communicate. So as you can see here, there's a nice method reference. But if you were to write a lambda like this, you completely lost the benefit of writing lambdas, because you got to stare at it now and say, oh, what does this do? And that becomes really hard to understand. And you cannot also easily change that into a method reference. It's hard to read, it's very noisy, leads to duplication, hard to test. You're going to have a poor coverage as well. However, if we write that as a separate function, as you can see, then we can easily call that in the lambda. We can even split that into multiple calls, and we can nicely write that into multiple lambdas and make it much more easier to maintain. So the point really I'm making here is it really comes down to discipline. And so avoid the temptation to put the curly braces right there. Because the minute we go that route, there is no end. It's a race to the bottom at that point, right? So what can I do instead? Take the time, and I'm a big fan of one rule I follow often. That is, make it work, make it better real soon. So essentially, you don't have to make it perfect in the beginning. So yes, I'm writing multiple functions, that's okay. But once I have a handle on this, I can come back and improve it. But if I create a mess out of it, it's really hard to really improve it at that point. So I'm going to say filter and push essentially, and I'm going to pass to this the predicate, I'll pass to it the element, and pass to it the downstream as well. Now you may say, gosh, you're already writing two functions. That's okay. Take your time rather than creating a mess out of it. So what do I do in the filter and push? It returns a Boolean, as you can see, and then it takes a predicate, it takes an element, it takes a downstream for that gatherer. So here I can say, if the predicate dot test is going to be on the element is true, then I'm going to say return downstream push the element. So you can see how we are saying if this element is acceptable, go ahead and push it downstream. And whatever the downstream tells you to do, take that and pass it to the stream above. However, if the element is not good enough, return, what should we return here? I'll give you a clue. True or false? Raise your hand if you think it's true. Okay, raise your hand if you think it's false. This is why this is hard. Because this is not democracy, I think, right? We cannot say, ooh, we got more votes on false, it should be false, or vice versa, right? Let's think about this logically. I'm a filter. I got a data, and I like this data, so I send it downstream. I got the next data. I don't like it, so I threw it away. Should I tell upstream, stop, don't send me any more? Or should I say, please send me the next one? See, we're not, still in doubt, right? Let's put false and see what happens. That's the beauty of programming, right? You can try anything you want as long as it's not going to hurt anybody. So that's beautiful, right? So let's fire it up. Notice what happened. That's the old filter. We got nothing out of this here. So that clearly shows that we were wrong. So let's go back and put a true. I like this kind of programming, right? Does that work? Why bother logic when you can try it out? So right there is the exact behavior as above. So we need to be able to logically say what's going on. A filter says, if the value is good, push it. If the value is not good, throw it away. If I push it, the downstream tells me it wants more. If I don't push it, if I threw away the data, I still need more data to be used. So I got to ask it for a true. So that's basically the idea here. And that's the entire code for us to implement our custom filter. Now, once you have this implemented, you can spend your time to refactor this to your content. You can leave it like this if you want to. Or you can say return in here and return a predicate.test on the element. If that is true, downstream push the element. If it is not true, just return a true. So if it's false, return true, right? So that could be optimized a little bit more if you wanted to. And of course, run the code. If you have tests, that's even better. And you can make sure it's working. But now that you can optimize this, you can then say, aha, I don't need to go that far then. I can simply be here and say predicate.test on the element. If it is true, then I can say downstream push the element. Otherwise, return a true. And in this case, I can simply remove this function altogether. So we don't need the curly braces that we once talked about because I couldn't see that far ahead, but I can refactor my way towards it. And in fact, the IDE says you can even improve this further, and it's up to you how far you want to go. And in this particular case, pardon me, you could say, hey, maybe I'll refactor this into, maybe I can say this is going to be something along the lines of, okay, it says simplify. I'll leave it to your judgment whether it's simple or not, right? So essentially, that's one more thing. That's one of the reasons I never trust the word simple anymore. Especially when somebody says, here's a simple solution, I'm like, oh boy, right? So your mileage may vary. You can leave it at that, or you can just fall back, or you can keep going and use the version that you are interested in. So that's giving us an example as to how we can implement it. But notice what we just did here. Did it work? So you can see it's the same output as the other version. So it's identical in this case. And when we received it, we tested, push it downstream, otherwise return true. So having said this, this is just an example of a custom filter. That takes us to this concept of the flavors of gatherers. Now, when it comes to the flavors of gatherers, we got 4 different angles we should look into. One is stateless, the other is stateful. So stateless versus stateful. So stateless, what does that stateless really mean? Stateless means that it doesn't have to deal with any of the neighboring data and information about it. Filter is stateless. I think we can agree to it, right? What about map? Stateless. What about limit? Stateful, because a limit has to know how many data has passed through. So state doesn't have to do with the data in the collection. It just needs information that it needs to collect. So a limit says, if I'm limit 3, what do I say? First one, go through. Second one, go through. Third one, go through, stop. So I need to count how many has gone through, right? So that's why it's stateful. Now, here is a question. Which of these 2 in your mind is simpler to implement? Stateless, definitely, right? So that's one angle. The other angle is sequential versus parallel. Can you run parallel when you have to run parallel, or do you have to run sequential? Now, having said these 4 things, here's something for you to think about. When it comes to implementing stateless versus stateful, who decides this? So stateless versus stateful, the domain decides this. So your business people say, we want to implement this. I don't think you have the luxury to go to them and say, you know what? I don't care about your business. I'm going to do what is easy, right? I don't think we have a choice, right? But sequential versus parallel, who decides this? You decide this. Why? Because the behavior is not going to be different, but probably the performance is going to be different. Now, one thing helps a lot to think about it. When it comes to performance, the question is not how fast the code is, but if the speed is adequate. That's what you really want to ask. Is the speed adequate? If the speed is adequate, you put more effort to make it faster. You got 0 benefit, but you got all the complexities you brought in. So the cost actually increases when you try to make it faster than it needs to be. So here is my first recommendation. We should never ever do this. Go to the business people and say, do you want this to be parallel? Because what will be the answer? Yes. Not only will they say yes, they will haunt you from then on. It's parallel, right? It's fast, right? And this is called self-inflicted wound. You just invited this. You sat there and said, my life is peaceful. I don't know what to do anymore. I want problems. So you go to your business and say, do you want this parallel? I can make it faster. They're like, you are the awesome person. Do it. You cause liability. The worst thing is you quit after doing this. And the other people are the victims now because they got to maintain this code that's unmaintainable. So I want you to think about this as what you should do and what you should probably postpone and avoid it. I want you to imagine a big C, the letter C, right? Think of the letter C. When you think of the letter C, I want you to now look at this diagram that's here. So draw the letter C on this diagram. So this one here, as you can see, is parallel execution. It allows parallel in a parallel stream. But if you're in a sequential stream, it's sequential. So that's the tip of the C, right? So put a C on top of that. So that's the tip of the C. The C curves here. This is sequential, but you don't have any state. The C comes down here. This runs sequentially, but it carries the state. And the C ends over here. This can run parallel and manages the state. Now imagine that C. This is the zone of smile. You are writing this code, you're listening to music, everything is good, right? This, you smile at people. They say hey, and you say hey back. This here, you are taking off-the-shelf Tylenol. You are taking, ibuprofen. Not bad. You toss a pill, you don't feel the pain, right? Here, you are in prescription medicine. Your doctor says, take this one, it's heavy dose, don't drive when you are taking. That kind of medicine. Here, there's a wire running into your back. You're taking epidural. You don't feel the pain. That's because you're being heavily drugged right now. Decide what you want to do, right? I like to be smiling, get my work done. So stateless, life is good. Stateful, pain increases. This is no reason to be here unless you truly find performance is a problem. And don't ever tell this to people because they will make it a problem. Just run it, see if everything works. Everything works, just go home. There are better things to do than to have to write that code because it's enormously painful. And I don't mind doing hard stuff, but it has to have value. And I would rather do other hard stuff that give you value than do hard stuff that don't give us value. So that's my recommendation is cautiously go towards this. I'll be here, I'll push myself here, but I would not go there until I absolutely have to. So having said that, let's talk about what this means to implement some of these. So we talked about the 4 flavors of gatherers, right? That's what we did. 4 flavors of gatherers. Let's look at an example of implementing this just to get a feel for it. So let's go ahead and take this collection of data that we have, and let's go to numbers.stream.forEach. And in this case, I am going to simply ignore the result that's given to us, right? So I'm just throw it away, nothing happening with it. Then I say peak, and I'm going to take this data and I want to output the data in the peak. But keep in mind, why would you use peak? For debugging purposes, right? That's what you use peak for. So I'm going to output a few dashes right there. So now, if I run this code, as you would imagine, things are just pretty straightforward. You printed 1 to 10 as you're iterating. However, if this is a parallel, let's say a parallel stream, when you run this code, there is no telling what the order is going to be. So if you're using peak in a parallel stream, and why are you using it? For debugging, you can know how annoying that can be, right? You're like, whoa, what is the order of the data anyways? So for debugging purposes, you don't want to change the parallel to stream and then debug it. You just want to be able to debug it. So wouldn't it be so cool to have a peak which is in order, right? So remember, you have a for each, or you can say for each, you can do for each, or you can say a for each, as you know, for each ordered, right? So you can use the for each ordered. So this will give you ordering even in the place of a parallel stream. Just like a for each ordered, I want a peak ordered, right? That's what I want to do, is a peak ordered. So in this case, peak ordered, well, I don't think there's a peak ordered function, but we can create our own peak ordered. So you say gather, and then you can just pass to it the peak ordered. So the peak ordered is our custom operation we want to perform. So what does the peak order look like? The peak order says, I'm going to take a gatherer, and where the gatherer is going to take an integer. Again, you can make it a generic if you want to. Nothing stops you from doing it. And then you can say, I don't have a state really, and I'm going to return an integer as a response. What am I going to take as an argument? Consumer of integer, again, it could be generic, and we'll say here is a block of code. I'll simply call it as consumer, right? So we're going to bring in the consumer into this. Okay, so what should I do here? Well, my job here is just report it. So consumer.accept the element. Well, pardon me, we need to create the gatherer. So we'll say return a gatherer of, and in this case, I'm going to say sequential. Why? Because I'm in a parallel stream, I want to run this sequentially, right? So that's why we say off sequential. Earlier we used off, here we say off sequential. I don't have a state, I have an element, and I have a downstream, as you can imagine in this case. So element, and then downstream, and what am I going to do with it? So this is consume, consume, and we're going to pass the element, and we're going to pass the downstream to the consume method. Well, what am I going to do in the consume method? The consume method basically says, I got an element and downstream, so return downstream.push the element that's given. That's all I'm going to do, right? So just passing that down to the caller. So you're just saying, I'm going to take the element, I'm just going to push it downstream and return it. Well, given that, you could probably say, hey, why not simply say downstream.push the element in this case. So element, let me fix that. So element, and I can just simply say, here's the element I want to push, so I don't really need that one. So let's see if that actually works. So let's go ahead and run that code and see what it's going to do. So basically, in this case, we are taking the collection of data, and that didn't work. Let's fix it. So in this case, I'm going to say, here is the peak ordered, and the peak ordered says off sequential, and it says I don't have a state, I have an element, I have a downstream, and I'm going to take this data given to me. Now I know what I did wrong, right? I got to consume it. So let's say consume and push. So essentially, let's pass the element and the downstream to it. And so let's take the consume and push. And what does that do? Here is the downstream dot push the element and then return that result. But before you do, consumer that you received up here, right? That's the consumer that you want. So let's go ahead and pass that here, consumer. So you're going to say, in this case, here comes my consumer. So let's say a consumer, of integer. Here's the consumer. And we can simply say consumer dot accept and push the element. So there's two steps, right? So you take the element, consume it, and push it downstream. So now if you go back and execute it, you can see that's the top part where the parallel peak doesn't know the order. And then you can look at the next part here, the order is implemented. So what's happening in this case? Streams have what is called an order that it implements. This order is actually not something you cook up. So that's why the term used is called encountered order. So what does the word encountered order mean? If you are working with a list has an order. However, if you work with the set doesn't impose an order. Well, your encountered order is what the stream tells you. On the other hand, whether you have a stream, a set or a list, if you did sorted, and then you have a stage after it, that sort is going to impose an order for you. So encountered order is whatever order is given to me. So this peak in sequence uses the encountered order in this case. So if the collection was a set, you don't have a guarantee of order for this. But if it was a list, you'll have an order, and it's going to follow that order. So, but how does it bring you the order? It brings you the order by putting sequential restriction on it. So what does this feel like? I'm a big fan of thinking about analogies. And so here's an analogy I want to think about. So when it comes to sequential and parallel, how does this work? So I want you to think about a roadway. So only look at this part right now for a minute. Here's a roadway, and you can see traffic flowing through these roads. You have 4 lanes, and there are 4 cars that are going. This happens typically at 4 in the morning when there's no traffic, right? So you can just zip through the roads. That works great. But what happens later? Well, when the more traffic enters, things get clogged a little bit. But to make things worse, every area that you travel has a construction zone. So here's a construction zone. What's happening in this construction zone? You have this sign that says lanes merging to 1 lane. This is a lot of fun to drive, right? So you got the cars coming here, and they got to hit the brake, and only 1 car can go through, and the others have to just sequence themselves. Once you get through the construction zone, your cars can speed up again. That's exactly what the stage of sequential does. So you have a parallel stream, data is flowing, and the sequential says, stop. I just want 1 at a time to go through. And then once you finish the stage, it can be parallel again, depending on what those stages want you to do. So this is the way to think about how the data flows through a stream. If you are in a sequential, there's only 1 lane, there is no concern of parallelism. But you're in a multiple lane road, all the cars in each of the lanes can keep going at the same time, but they have to merge in the construction zone. 1 car goes through, and then on the other side, you can speed up again. So that is basically what off-sequential does. So in this case, the stream is parallel. However, when you come into that stage, you are being sequential, and you're sending 1 at a time. So that's basically the behavior of the off-sequential. So what we did in this example is we first implemented this, which was stateless, and it was parallel. Then we implemented this, which is stateless also, but is sequential. So not too much of an effort, right? Going between those two, not too bad. But what's going to happen the minute we come here? That's when we're going to bring the state for us to work with. So that's peak in order. But what if you want a map with index? In languages like JavaScript, you can do map, but a map will also give you not only the elements in the collection, it will give you the index of the element as well. Java doesn't have a map with index. Hey, but what if my business says, as you map through the elements, you need to also print the index along with the element? I will say there is actually a non-gatherer approach already for this. That's a challenge, right? You could start iterating through the range of values. And when you have the range, you have the index already, and you can pull the values out. But in all fairness, you say, but what if this is not a predetermined collection? What if this was a collection where the data is being produced like an infinite stream? Okay, fine. That's really, really hard to do it without this, so maybe there's a use case for it. So you have to really analyze that to determine whether you can do this. So map with index. Now, as you can imagine, the map with index is really stateful. Why is it stateful? Because I got to keep incrementing the index as I'm flowing through this, right? So that's a map with index. So how is this going to work in this case? So here is the collection of data. Actually, let's do names is equal to list of, let's go ahead and say some names I want to write over here. So there's a bunch of names, but I want to print these names, but I want to print them with, let's say, the index. So let's do two parts here just to feel how this looks like. So names.stream dot for each system.out, and we'll do a print line on it. But within this, we'll do a dot map, and the map is going to be string to uppercase. So I want to convert it to uppercase, and I want to print it. So as you can see, all the names are being printed in uppercase. Okay, great. However, I really want to print them with the index. So the question is, how can I print them with the index, right? So we'll say map with index. So that's what I want to do. I want to perform a map, but I want to perform a map with index. So we'll do a gather as a call right there. So we'll bring in the gather, and the map with index is the function we're going to perform that mapping, as you can see right there. So we are implementing our own custom gatherer for mapping with the index. So the idea here is when I print it, I wanted to print not just the names in uppercase, but a 1 dot and 2 dot and 3 dot, and so on, if you will. So the question is, how can I really make that work in this particular case? So let's give it a try and see how we will bring that one together. So what I want to do here, this is going to require a little bit more effort. Remember I said you're no longer in off-the-counter medication, right? You're in prescription drugs right now. So put your seatbelts on. It's going to take a little bit more effort. We're going to do this sequential because that's less painful than going parallel. So map with index, what are we going to implement? So here is a gatherer we're going to bring in. So let's talk about what we're going to implement in this case. So you have a string, which is the data that's coming into this particular operation. So that's great so far. However, this one needs to implement a map with index, but what is the return type of this function? This is where things get a little bit more gnarly, if you will. So I'm going to say, let's actually go a little bit more intense on this. So I'm going to say this is a generic TNR, right? Might as well generalize that. You can use it as a string. Nothing says you cannot. But I'm going to say this is going to be a type T. Okay, but what is going to be the remaining two arguments? We've been skirting that question mark, right? We didn't care about what it is so far, but it's time for us to think about it. So what is the state? The state is an index, right? So the state is an index because we need to keep counting the index as to 1, 2, 3, and so on. What is going to be the result of it? Well, remember, I should be able to emit not just the value, but I need to emit the value and the index. So this is going to be value with index. And the value with index is going to be of type R, which is the transformed value. So you can see where this is getting a little bit more intense, right? So we have an element coming in. We want to output an element, but the output element is a value with the index. And the value is the transform value. Index is going to be inside of that. What is the index? That's going to be the index, which is the state we want to work with. Well, what's the parameter to this particular function? Aha, we know what that is. From here, we know that a map takes a function as an argument. So this is going to be a function, t comma r, and that's going to be your mapper that you want to really use. So there comes the function you're going to be using as well in here. So that's your mapper as you would expect. Okay, so what's the next step? Before we go further, of course, we need the index and we need the value with index as well. So let's think about what the index is going to look like. So let's go over here and let's create a class called index. So the index class, what is that going to provide for us? Well, the index class, as you would expect, is going to contain the counting index, right? That's your state. So I'm going to say private, let's say private. This is going to be int position, or the index is equal to 0. That's your initial value. We start with an index 0. But we're going to say public int, and I'm going to say get, and we will call this as increment, and this is going to say a return. And what am I going to return at this point? The position plus plus. It's a post increment. So you return the value and then you increment it, right? But when you look at this, the first thing that's going to come to your mind is you're going to say, wait, stop. You said we are doing functional programming. Are you serious? You are mutating something. If that thought comes to your mind, that is genuine, right? Because we freak out when we see mutation in functional style code. So I want to pause here for a minute and talk about mutation and functional programming. So let's talk about that. So in functional programming, right, we often say programming, we do not want to mutate. So that's very clear, right? That's a thing that we follow. But we have to know, right? But what is mutation is the question we want to ask. So here's my recommendation. I'm going to say mutation is like changing clothes. I sincerely hope everyone in this room changed their clothes before coming here, right? If you didn't, there'll be a big gap between you and the person next to you because it's going to be smelly, right? Well, so we all change clothes. What I mean by this is we all should change clothes, but please, I would request you, don't do that in public. So that is it. So mutation is okay, right? So essentially, mutation is okay as long as no one sees it. So that is the key. So in other words, do not make mutation visible outside your functional pipeline. So that is what we really mean. So mutation is not bad, but mutation in a way it's visible is bad. So can I mutate data? You can do all you want. Just don't take a shared variable and then start mutating it. Because a shared variable is visible from the outside. That is not something you should do. So mutation is okay as long as it's an internal data. You shouldn't mutate a visible external data. That is the key. So when you look at this code, you say, oh my gosh, you're mutating it. Yes, but it's an internal data. I'm not going to make this visible outside, right? That's the key. So in this case, we have the position, and we are incrementing the position, returning the value, and then incrementing it. But this is not something we just put out for visibility outside. So that is our class index. Then we are going to create, in this case, in addition to it, a record. Records are nice to create to pass data around. What is this record? Value, with index, right? That's what I call it, value with index. And this is going to be a type T or an element E, doesn't matter what you call it. It takes a value and it takes an index as an argument as well. So you have an index and you have this particular value that you're going to pass. If you really, really wanted to, nothing stops you from just passing in int as well. You could do that. We can refactor that if we need to. But then what am I going to do? I'm going to provide an override right here. So here's my override. And this is going to be a public string to string. And remember, records already produce some useful output, but we're going to change that. So what are we going to change that to? I'm going to simply say return, and we will return a string. So a %s and then maybe an index, right? So %d dash dash %s dot formatted, and we'll provide the index right there. And then we will actually provide, so for this index, right, it's going to be the value of the index, whatever the position is going to be, we need to bring that in. And then we are going to say, in this particular case, let's go ahead and provide the value that we are interested in printing as well. So we have the index and the value that we want to output at this particular point. Okay, so far so good, but how am I going to use these two values? Now, as you can see, this doesn't have to be an index, it's just an integer, right? I don't need to carry that index, it just can be an integer value that I want to print here. So far so good. Okay, so far we got the index, we got the value at index, time to really work on it. So back here, we can say gatherer.offSequential, and what are the things it's going to take? Notice it's going to take index as a value. So the first argument you're going to pass to it is index : new, and you're creating a new index because you need an initial state to feed it, right? So that's your state of 0. So you create this, your index is 0 right off the bat. Then you're going to say, I have a state which is index. Remember, we used an underscore in the past. Now we do care about the state, so index element and then downstream are the 3 values you're going to be using. So that is your off sequential that's going to produce that data. Well, what are we going to do within this? Well, in this particular case, we are interested in navigating down through it. So downstream dot push. What am I pushing downstream? Remember, I'm a map. My job as a map is to transform data. So I'm going to push to the next downstream the transformed data. But I'm not just going to push the transformed data. New value with index. And in this case, the value is the element transformed using the function. So mapper dot apply on the element. So that is going to be the first argument I send to the value with index. The next one, I have to increment the index. Thankfully, the index is given to me right there. So index dot get and increment. So that's basically what I'm going to pass down as well into this particular stage. So we have an index new, and then we also took the index, took the element, took the downstream, and we are telling that I want to push to the downstream the value with index, where that's going to be the apply and then get. Almost there, right? Almost there. But this new, what's the problem with it? Cannot resolve the constructor for index, it says. Well, the constructor should exist for the index, so that should be fine. We'll see why that's complaining in just a minute. But going back to here, you may have to do a couple of things to help the compiler at this particular point. So this guy here, what is it going to return? This is going to return a gatherer, and here comes the index that we are using. And this is the value with index r, that's the integer itself it's going to take, and the t, so that should be just fine in terms of the gatherer that we are bringing in here as well. So the question then is, what am I going to pass here? Sometimes you may have to provide a little bit of help. So when you look at this here, it says stream value with index, so that's a good thing, right? That's what you get out of this as you transform. But what's going to be the type of the data that gets transformed? So this is where the compiler may need just a little bit more help from us. So you will have to go here to map with index, and you want to say sample dot, and this is going to be a string you are passing to it, and a string you are returning as a value, and then a map with index. That's going to be the function you are calling at this particular point, and you're passing a string to uppercase function, as you can see right there. All right, so let's start with that and see why it's complaining, and we'll figure out what it says. Oh, so that should be a non-static variable, cannot be instantiated in a static context. Pardon me. So let's see why that's giving us the error. So non-static variable cannot be referenced in a static context. So that's just the constructor we are calling, right? All right, let's take the hard step and see whether we are able to resolve it in here as well. So this is going to simply say new, and I'm creating an object of the index. Let's see what error that gives us. Most likely it's because it doesn't know what the type is. So essentially it says cannot be referenced in a oh, okay, I think I know what's going on. I should probably define this as a static class, I'm assuming, right? Because it's inside the particular object. Well, it doesn't have to be part of that member. There you go. All right, so let's see if that does anything useful for us at all. So right there is the map, as you can see, and then we have the index right here, right? Dory is 0, as you can see from the data, and Gil, and then Bruce, and so on. And just to emphasize this, if we go back here, and you can say, just for the sake of fun, to know it's doing the job, a dot filter, and I'm going to say this is going to be a name that is going to come in, and I will say, in this case, name dot, let's say length is equal to 4. In the output, you can see Dory, Gil, and Nemo. Well, let's grab this filter the way it is and drop that filter right there in the previous stage, run the code again, and you can see Dory, Gil, and Nemo. So the index is doing the right job, right? So essentially, let's talk about what the code is actually doing. So in this particular case, you can see that we created an index. And that index that you created right here is being initialized right there. Let's take the time to understand how this works. So essentially, in the case of the gatherer, when you said, I want to create a map with index that's returning a gatherer, where this gatherer has an element, but it's got a state, which is the second argument, in this case index, and then the third is the transformed output. In our case, we are doing a value with index. So the record, as you can see, thankfully, has only immutable values, right? So it's got a value for the element, whatever that element is. You got to make sure it's immutable. And the index is an integer, so that's pretty safe. And we're just printing out the results. That's all we are doing. So back here, what does the stage do? The stage basically says, I'm going to come in here and take an initial data, and when the stage is ready to run, it gives you the element for that stage, it gives you the downstream reference, but also hands off a reference to its internal state, which is the index. What are you doing? You are saying, all right, thank you for that. I will take the data, I will push that to the downstream as a value with index, where I will take the data, transform it into this using the mapper, send that to the value with index. So the value with index receives the value, which is the text in uppercase. And then I will pass to it an index where I increment that index and then pass the integer value to value with index. But when I do, I'm actually incrementing that index that was given to me in the call right there. So you have the parameter that's coming in, and you modified that parameter to a value. You may say, gosh, is it a good programming practice to modify parameters? No. But this is an internal piece of code. You're not providing this from an external call. So nobody is sending this to you. Nobody is directly making this call. This call is purely internal to the stage, right? So this index is being modified when the call is made the second time that same index is given to you. So you are continuing to use the same index. So the stage basically says the following, right? So this stage says, I'm sitting right in the middle of the stage, and right in the middle, it says, I'm stage 3, for example. I'm going to be called repeatedly, but my index is my own member within that stage, right? That's internal to that particular stage. And that internal index is being used repeatedly, and you have a reference to it, and that reference is given to you as part of that call. So you get the index, internal reference, you have the element, and you have the downstream given to you as well. So that is basically an example of using a stateful in this particular case. Now let's think about this for a minute. When you have a stateful, what's happening in this case? The stateful says, I am going to have to maintain that state as an index. So it's your responsibility to manage that state and keep returning it. You can also think about how a limit would be working. A limit says, I've got a count, and every time an element goes through, I'll keep incrementing the count. If that index count is equal to the limit given, I will send a signal to stop sending the data after that. So that's basically that state that you see up there that you're maintaining with this as well. So back to here, we just implemented this part right in there. So that's running sequential, and but it's also stateful, so we implemented that particular part. You say, all right, what if I really want to implement all the way parallel? Let's talk a few minutes about full parallel for a minute. Before we talk about the full parallel, let's understand something else that we are probably familiar with and understand how that actually works. So when you say numbers.stream.map, and just to entertain this thought, element times 10, let's go ahead and say dot reduce. And we say 0, comma, integer, and we'll say sum. So this is going to return a result, as you can see. And what is the result going to be? The result is going to be the sum of all the values multiplied by 10. So when you run this code, it's 550, right? So that's the result. However, we need to understand how reduce actually works. So here's a question for you. I have two options, right? I want to add 10 to the result of this. I have two things I can think of. I can do the following, right? So to add 10, I'm going to put 10 here. And that way, I can add 10 to the result. We had a 550, right? So that should be 560 as a result. Yay, that's 560. That's one option. Another option you can think of is not do that, but instead say reduce with a 0 as we did, like so, and do a plus 10. So right there, that's going to be a result of 560 as well. So my question is, this is exhibit A, and this is exhibit B. So the question is, should I choose A? Should I choose B? Or, dude, it doesn't matter. On Wednesdays, you can choose one. Tuesdays, you can choose another. What do you think? B. Should I ever choose A? Aha. When it's sequential, you could. But somebody makes it parallel, and all hell breaks loose, right? So let's understand the consequence of this. So this is why these operations are called as monoids. So what does that mean? When you go back to this, let's take this one here, where you're adding 10 to the end, right? So I convert this to a parallel stream and run the code. It's 560, right? Not a problem, which is what you were expecting as well, which is 560. However, if you take this one instead of the other one and run the code, the result is 650, right? You're like, gosh, why is it 650? And maybe, right, depends on how it's going to execute moving forward. I'll put a 0 in there just for the sake of fun, right? And I'll put another 0 in there. And as we know, the 0 shouldn't make any difference, but it gives you bonus, right? Right there. So the question is, what just happened? So let's understand how this actually works. So imagine for a minute that I want to total the age of everyone in this room, except me. Because if you include me, that may be overflow. So we'll ignore that. So let's say we want to total the age of everyone in this room. We could give this person here at the very end a value of 0. They can take a 0, add their age. Now it's their age plus 0, give to the next person. They accumulate their age. We can slowly watch this go through, right? And the age count is going through the room one person at a time. So everyone receives the age of everyone to their left, adds their own age, and sends it to the next person. Now, that is sequential. Great. Now I want to do this parallel. How are we going to do this parallel? I'm going to ask every single row in here to do the same operation. So you're going to start with the 0. So are you, and so are you, and so is everybody in the edge seeds in here. Similarly, everyone in this edge and everyone in that edge. Well, we all can compute the age in parallel. Now, at the same time, give or take, we have the results of every row in the room. So then we can look at this section here and say, everyone on the edge here knows the total age of everyone in that row. So we can then take this particular row here as a row, and we can then say, let's split that in, right by the divider. You all compute the total, and way over there in the top, you all compute the total. But what should I give as a value to start with? It better be 0. So when you give a 0, everything is working just great, as you can see. But if you give a 10, what happens all of a sudden? If you're doing it sequential, you start with the 10 and add your own age, but then as you continue, 10 was the only one that was added. But the minute you make it parallel, we started every row with a 10. And all of a sudden, we have an inflation on the age, right? Pardon me. So in other words, the question is, how does reduce work? Reduce works in parallel when run in a parallel stream. Excuse me. So essentially, what's happening in this case is the reduce is saying, just as an example, right? It may be split differently under the hood, but reduce is saying the following. It says, take a 0 and work with 1 plus 2 plus 3 plus 4 plus 5, and at the same time take a 0 and work with 6 plus 7 plus 8 plus 9 plus 10. So it's going through the 2 in parallel, right? Not considering these zeros, if you will. Just as an example. So it's working through those 2. And this gives you partial sum 1, and this gives you partial sum 2. And then it takes these 2 partial sums and totals them using a 0 again. So 0 plus, and then partial sum 1 plus partial sum 2. So the moral of the story here is that is done in parallel as well in terms of how it's executing it. So as a result, in this case, again, we are starting with that 0 and adding that to that particular 2 values, right? So the moral of the story here is you are going to run things in parallel, but you need to know what to really bring in as a state. And so the first question you want to ask is this operation even parallelizable? Just because you have the power to parallelize doesn't mean you can parallelize everything. For example, a reduce with a sum, you can parallelize it. But can you take reduce with subtraction, and can you parallelize it, right? So you need to really ask the question, is this parallelizable? If it's not parallelizable, the answer is you cannot go there because it'll be an incorrect solution. And what's the point in running code really fast to produce a wrong result? It wouldn't make any sense, right? So that's the first question you want to ask. If you say, oh boy, it is parallelizable, then what are you going to do? Notice this one in this case. If it's parallelizable, you will have to know how to take them in chunks. So this is why this is more complicated. This group here runs in parallel to produce this sub-result, and this group here runs in parallel to produce that sub-result. Then you have to take those two sub-results and compute to send it to the next stage. That's where the complexity really comes in. You have to work through all that logic to get that done properly. So, in other words, going from here to here is not really a trivial jump. To go from here to here can take a lot of effort. To get it correct is hard. To be able to know that this actually works becomes really difficult. So here's what I would recommend. Let's say you are set to write a code and they tell you, you got to implement it and it better be really, really fast. You just give a nod. Don't commit to anything. Don't jump into parallel unless you really want to get hurt. And you will have not any code that's working properly. What's the point in doing that? I'm a big fan of incrementally developing code. So my recommendation is, forget about parallel, just implement it as stateful sequential first. Hey, it works. Here's a stateful sequential code, and it runs, produces the right results. Then ask the question, is the performance adequate? If the performance is adequate, be quiet. Don't really go around telling people, I could parallelize it, right? That's not going to be fun doing that. You can go around telling people, I'm done. It works, right? That's it. You don't have to demonstrate this to anybody. If the performance is not adequate, then find where the performance problem is, understand that first, and see if you can improve it. You say, you know what? I looked at everything. I still need to really parallelize this because I need better performance. Ask the question, is this actually parallelizable? Logically speaking, does it make sense? If the answer is no, there's no point going there. If the answer is yes, then and only then move towards this. But stopping here as a stopgap helps you to more thoroughly understand the problem, to create a code that is easier to get it working and then transform to parallel. And as you would realize, when you go towards this, you need to really think through how these data have to be brought in and merged. That can take a lot more effort as well, so don't take that too lightly. So my recommendation is take it in increments and work through it rather than jumping straight to parallel, because that's going to be really, really painful in general. Excuse me. So as we talked about, the other thing you need to really get comfortable with is the fact, like I said earlier, to understand the behavior of a stage. And just to reiterate, you are in a stage, you are receiving data, you do your processing, and you push the data to the next stream. And the next stage, downstream. And the downstream tells you its desire, that it wants more data or not, and you're taking that and forwarding to the previous stage. And in this case, you might also have to make your own decision, because sometimes you realize, for example, if this is filter, you're never going to return a false, you're always going to return a true, or what the downstream says. But if you are a limit, or if you are a take while, you may return a false yourself because you reach the limit or you found an element that doesn't satisfy the predicate. You can say, stop, don't send me anymore. So if you're a take while or a limit, you might produce a true or you might produce a false depending on the situation. But that is something also you need to think through. And what is the responsibility of my stage? Should I say false or should I say true? Or should I simply only pass what the next stage is returning? You may have to evaluate that as well. That becomes your burden also in making sure things are actually working as they are expected. So that kind of brings us to the end of this discussion in terms of what it takes to implement gatherers. If you're interested further, you can read, I've got 2 chapters in Cruising Along with Java, which is what I was showing you as the picture over there, to talk about how this can be implemented. And so the whole idea behind this is that you want to really implement your custom gatherers. But the words of caution I mentioned, to reiterate, ask yourselves if it needs to be done. Second, can it be done using built-in functions? If it cannot be done using built-in functions, can I use it with pre-provided gatherers? If that's not an option, well, then incrementally approach it. Don't try to jump into most complex solution, because that becomes enormously complicated, and life is no fun. If we want to take that kind of complexity, it becomes really hard to maintain, and there's really no reason to endure that kind of pain. And like I said, if you're interested, please take a look at the Cruising Along with Java, and I have 2 chapters on gatherers alone, and you can take a look at it. That's all I have. Hope that was useful. Thank you.